I do kind of want to just kind of go over again the general basics of your nucleophilic addition. Okay, so if you see a carbonyl anywhere, doesn't matter where, any part of the exam, you should be thinking at least 2 steps. Okay? And one of the things that you should be primarily concerned about is that when you see a carbonyl, you see what reactivity. If I just draw a carbon-oxygen double bond, what reactivity should you immediately be thinking of? So we could go with the type of reaction, but I was focusing more on the type of reagent. Carbonyls act as electrophiles. We've got a pretty sizable positive charge on that carbon, or partial positive charge, so that when you shift to the next step, you should be looking at that reagent and saying that reagent is acting as a nucleophile or, try again, a base. If you have a nucleophile, it will act as a base. Okay? So where I'm noticing this pop up and people getting confused about is that if we have an ester, we still have that positive carbon as a possibility. Okay, which means we still have an electrophile. If I want, say, that alpha position with its potentially acidic hydrogens, if I want those to be removed, what do I need to react this structure with? A base. So I would want to add a base. Well, are all bases the same? No. So we have to be very careful about what base we choose to use. Most typically, when we choose a base, we try and choose the cheapest base that'll get the job done. Okay? Cheapest base, probably hydroxide. Okay? Really straightforward and simple. But when we have a base, what can it also act as? A nucleophile. So if we go through and add, say, hydroxide, that's also a nucleophile. So if we now go back and look at the carbonyl chemistry, well, the carbonyl, the first thing you should think about is that positive charge on your carbon. As a secondary effect, we can shift to the base, or sorry, the acidic hydrogen being positive, but that's typically a secondary effect. So we've got 2 competing reactions that can happen within this. If I want only the hydrogen to be removed, is hydroxide a good option? No, because if it attacks the carbonyl carbon, the structure changes. The end result is different. So the base that we actually choose to use needs to replicate our ester as best as possible. So you'll notice that our leaving group on our ester, or our ester structure, is the same as our base that's being added. As long as those pieces are identical, we're going to maximize our results because it's still going to act as a nucleophile. But when it acts as a nucleophile, it does nothing to the overall structure. Okay? So instead of having 2 possible sites of reactivity, we really just have 1. Now we can make sure to drive our yield to the highest possible yield without all these other kind of side reactions happening. So what we want to do is focus on trying to do just one thing at a time. Right? And only that one thing. This becomes exceedingly or more prominently difficult when you move into the synthesis questions, because the synthesis questions are not phrased which of these work, it's which of these work best. Okay? Hydroxide could still possibly pull off that hydrogen, but it's also going to do some other stuff. Okay? So what you're trying to do is focus on the best answer. And nobody likes the best answer questions because, yes, you can have a bunch of correct answers present. Right? You are going to have to decide of those correct answers which one is the best. So look for those evaluations. When we go through and look at our nucleophilic addition reactions, if we clear everything away, what we'll end up finding is that we have our electrophilic carbonyl followed by some nucleophile. All the way through these. Every single one of these has the same concept happening within it. Okay, so our very first step is that the nucleophile comes in and attacks. Right? This does not mean remove the hydrogen from the nucleophile. When could you remove the hydrogen from that nucleophile? I'm not quite sure I heard that right, so I'll just say the answer and you guys can all be happy or sad if you got the answer right. You need to be in a strongly basic environment. It must be a strong base. Why? What's the acidity of an alcohol? That is the acidic atom, but what is the acidity? Is it a strong acid? No, it is a very weak acid, which means if I want that to be a strong nucleophile, okay, to make it negatively charged, I have to add a ridiculously strong base to remove that hydrogen so I have my strong nucleophile. Okay? So don't skip steps. Okay? We need to have these certain conditions met before we can advance. So our nucleophile in this case is a weak nucleophile, which works out okay in this circumstance because what's the deal with our electrophile? Is it strong or weak?
Oh, strong.
Okay. So there's a couple options we could go here. You could call it weak because, what was your reasoning?
It's still a partial positive charge.
So
It's
you're-
not a formal positive.
Yeah, so your weak argument is that it's not formally positive. Okay? But it's usually fairly rare to see things formally charged anyway because we're trying to add things as neutral as possible. So if we go through and look at that structure, we have the carbonyl carbon, already electrophile. Then we add a chlorine to it. What is chlorine going to do to that carbon? Make it more positive because chlorine is electronegative and draws that electron density away. So we're identifying those charges. Our nucleophile can attack. So in our very first step, what we end up doing is an addition because we lose the pi bond. Okay? The conditions of when that addition step occurs may vary depending on the strength of our individual species. If we have an acid or a base present, we may be protonating or deprotonating first. Okay? But we're going to get an addition happening as our very first step. What happens next? We'd end up with a tetrahedral intermediate, which is unstable, and it then falls apart. Okay? To reform the carbonyl double bond, which means we now have done an elimination. Okay? So our nucleophilic addition or nucleophilic addition reactions or conversions are sometimes referred to as addition eliminations because mechanistically that's what happened. We went through and did an addition followed by an elimination. The overall result, as I'm thinking you were about to say, looks like a substitution. Okay? But mechanistically, it has to go through an addition followed by the elimination. So we're getting that stepwise sequence happening out of this. Does it lose a hydrogen? Okay, so it's all about focusing on the chemistry, on where everything occurred. So we've got a variety of places that we can look at where that chemistry occurred. Most typically, we're looking at it around what atom? Carbon. Why carbon? It's organic chemistry. Okay, that's why we'll focus at our carbon. So the only carbon that changed, okay, was in our acyl halide. Did its oxidation state change? It does not change. So when you think about oxidation and reduction, you need to look at where your center of reactivity is. Okay? In this case, it's that carbon. Okay? You might look at it and say, well, it's gone from chlorine to oxygen. True, but when we're looking at oxidation states changing, we're looking at changing for a different balance of electronegativity. Meaning if I trade out chlorine for hydrogen, now I've done a reduction reaction because hydrogen is lower in electronegativity than our carbon. So if we do exchange that, we do see a substantial change in our electronegativities. Right? In this case, we go from chlorine to oxygen. And yes, oxygen is more electronegative, but both are more electronegative than carbon. And if we think back to oxidation and reduction, our official rule is, are we exchanging an atom that is more or less electronegative than carbon? Okay, so in this case, we didn't really do an exchange because it's a one-for-one trade. Okay? Then we had all of the fun reactions that came out of this, your acyl halide reactivities being our most reactive. Our Grignards and our Gilmans, which we talked about, are all our acyl chlorides, our acid anhydrides, doing pretty much the same thing. And then we'll move into our esters and amides. One thing I want to talk about real quickly, actually. Why do acid anhydrides react similarly to acid chlorides? Draw up an acid chloride real quickly, or an acyl halide. Why does the anhydride react similarly to the acid chloride? Okay, but all of our acid derivatives are going to have the same center of reactivity. Okay, I like that theory. It's a good option, so let me draw in a counterpoint. What functional group do I have now, bottom left? Ester. Are esters as equally reactive as our acid anhydrides or our acyl chlorides? No, drastically different chemistry. So, try again. Why are acid chlorides and our acid anhydrides similar in reactivity? Has to do with the stability of your products. Okay. Chloride is a fantastic leaving group, and the leaving group in the case of the acid anhydride is it's a carboxylate which has resonance stabilization. Okay. Both of those generate really, really good leaving groups. Both of those species are extremely reactive. The chlorides are more reactive because why are chlorides really good leaving groups?
It's a halogen. It holds a negative charge.
Well, that's still going along the same lines of it being a good leaving group. You're right, but why? Getting to the right idea, except in the case of the anhydride, it's oxygen, which is actually more electronegative than chlorine. So your electronegativity argument doesn't quite hold water. Okay, Tui, I'm going to put you on the spot because you've asked about this. And we're determining all forms of reactivity. First step. Yeah? Your turn.
Substitution.
No. Sorry, I know it's mean. Talked about it on Friday. No.
Is that big chart in front of the wall? Number 3?
The big thing I had in the corner of the white ball.
When what determine?
You mean the size?
Getting to the right idea. It's not the first thing you look at.
Yeah.
All organic chemistry can really be summarized down into one setup. The first thing that we're going to look at, well, ultimately, all organic chemistry, our overarching theme is stability. We drive to be more stable. How do we look and evaluate stability? Very first thing we want to look at is charge. Okay. Is our atom charged? If it's charged, that's necessarily now more reactive or what's that? Less stable. More reactive, less stable. So we just look, is there charge? Well, in the case of both our acid chloride and the acid anhydride, do we have charge? Try again. Yes, we have charge. So we're just looking at the piece that's left over. Right? Charge comes out of both of these. Okay? So based on our first approximation, they are both equally stable or unstable. So no real analysis. It's the next thing we look at. Close. I want a little bit more information there. You're right, it is size. Nope, it is size. Size of what? It's the atom effects. So if we look at an atom effect, we'll look at the size of the atom holding the charge. So what atom is holding our charge? What atom are we trying to compare reactivity of? Well, chloride versus oxygen. Why do I not look at the carbons or the other oxygen in the case of the anhydride? Sort of. Yeah, maybe I'll just straight up accept that. We're looking at stability. We're trying to find the most unstable thing possible. So why do we look at the oxygen and not the carbon? What's rule number 1? Charge. Why should I bother to look at the carbons or the other oxygens if they aren't charged? We're only going to go to the place where charge has been built, so to speak. So we can then look at our size effect, chlorine versus oxygen, which is bigger. Chlorine, what does that do to the stability?
More stable.
Makes it more stable. Okay, well, if that's more stable than that second reaction, which one of those is going to produce the most product? The one with the chlorine, because it's generating the most stable product possible. Okay. Do we know what it's reacting with? Is it relevant? No. Okay. All of that would be secondary information there to ultimately confuse you. We could go through, if we were going to ask this question, you would notice that what it's reacting with in both of these cases would be what? The exact same thing. Why? Because if we start changing what that species is, that can drastically change our outlook on how this reaction would work. Because now we're not just evaluating these two negatives, we're evaluating another sequence of reagents. Right? What if we don't see a difference at the size comparison? What do we move into? Nope. It's still an atom effect. But now what we'll look at is electronegativity. Okay? If we still don't see a difference, where do we then look? Okay? Cheating, you copied it already. Can then look at a molecule effect. How does the molecule change the stability of that atom? Well, in this case, we can say resonance is the next thing we'll look at. I don't know if I actually wrote this up last time. What does resonance equate to? It is going back to stability. It's the same thing as size. Because what are we doing? We're taking an electron from one atom and we're scattering it over multiple atoms, meaning that electron density is spread across a larger area, much like if we'd put that electron density across a larger atom. So it's ultimately a size effect. It's the exact same thing that we saw for our atoms. There's another molecule effect. The molecule effect also gets a fancy name. What's that fancy name? You can get induction. Well, what's happening with induction? It's an electronegativity effect. Okay, pretty much, again, the same thing as our atom effect. We come up with these fancy names for it so everybody thinks there's something different. They're exactly the same thing. Okay? If you go through and look at ranking acids, ranking bases, okay, doing any kind of the reactions that we've gone through and done, you can probably use those first 3 rules for every single question. Right? Because our whole goal is trying to strive for something that's stable. Well, what's stable? Anything that's neutral. So find the most positive, find the most negative, and do what to it? React them. Okay? If we're asked to rank acids, what do we have to do? Well, we need to know something about our definitions of what makes an acid and what makes a base. If we know those definitions and we understand these first three things, all of our ranking is now fixed for us. We just follow that rule set. We're not changing the rules at all throughout the semester. I will say we do throw in some exceptions every so often, like anything to do with the metals. It's just a mess. Right? They're still working on fixing that. If you go all the way through this and you still haven't seen an effect, okay, then they start throwing in other names and terms at you just to make it even more confusing. Okay? Last one that we'll mention here, well actually, I'm going to do subcategories. I like to call it the oh crap category because at this point we really are pulling at straws and hoping for some kind of difference. So on a multiple choice test, coin toss, guess, put it down, move on. Okay? You've already spent enough time thinking about all the other effects, so you can just advance. Okay? What I classify under the oh crap category would be hybridization. It's the big one that you see typically. Okay? Which is really just an advanced, super advanced application of what? It's not size. It's an atom effect with electronegativity. Okay, it's the same thing. Okay? The only reason I use the O symbol here is I've had a colleague that came up with cardio or something like that, with what each of the different rules are for ranking acids and bases. It's not just acids and bases, it's everything. Everything comes back to the same principles. Okay? Questions on any of that? Okay, exciting. Let's move on. Esters and amides. Here's your extra mechanism only because it gets named and it's very commonly done in labs. I just find it kind of a boring lab, so we didn't do it. So what's happening with this mechanism? Okay, minimally, how many steps are we going to have? Why 2 steps? We got a carbonyl, and not only do we have a carbonyl, if we look at our overall result, what appears to have changed to that carbonyl? Appears to have done substitution, which means we're doing an addition-elimination mechanism, which means we've got at least 2 steps. We have to do the addition, we have to do the elimination. Okay? So, where do we start? Charge. We find the absolute most reactive thing present. Once we've got that, we then try and zero in on our next step. So what's our most reactive thing? Try again. The acidic hydrogen sitting right in the middle of that reaction. Sometimes it's added as a catalyst, sometimes not. Doesn't matter. It's still the most reactive thing there. That's our reactive positive. Okay? So if we've now got a positive, what do we need to find? Where are our negatives? Anybody see a formal negative?
No.
No. So that becomes a bit dangerous. Now what do?
Partial negatives?
We can look for partial negatives by looking at atom effects. Where are their lone pairs? Lots of oxygen lone pairs. Okay. 3 possible places we could react. What do we do now? No, we don't even need to do that. What's that? In any other time in the semester, I would say exactly what you just suggested, Sarah.
And see what you get.
React them all. Do every single one of them and see what happens. Okay? We're at the end of the semester. We only got a week to go through and do this. We're going to react. Added an extra pair of electrons here. Why react the pi bond? It's our highest energy source of electrons. And this isn't just a standard alkene source of electrons. We're looking at the pi bond in the carbonyl. Why? What's the difference between the oxygen in our carbonyl and the oxygens in the other places? What's that? Yes. Why is it more polar? It's our oh crap rule. What's the hybridization of that oxygen? sp2. It is more S character than any of the others, which means it is more electronegative, which means that pi bond has been polarized extremely towards the oxygen. What charge is the oxygen? It's our biggest negative in our structure. Okay. If that's the biggest negative, what should react with our positive? Our biggest negative. And we can now start to push this reaction along. What happens if that reacts? Well, it depends what arrow we decided to show. I reacted it with the pi bond, so I'll hold true to that. Well, that's never the structure shown. Yeah, it is. You've got a resonance structure that is also present. The resonance structure is most commonly the one that is shown. Why? What's that? Huh? I still don't know. I'm not hearing any of that. Easier to look at? No, not quite. This goes all the way back to first semester when we first drew out Lewis structures. The first structure I drew, not a good Lewis structure because carbon doesn't have its octet. Whereas if we look at the second structure, every atom has its octet. Okay? So typically when these reactions are drawn or these mechanisms are set up, we draw it in such a way that we produce the product that is the best. Is there a difference between either of those two structures? No, they're resonance. They are one and the same. Okay? And so depending on how you want to evaluate and approach a problem, you may end up with slightly different structures drawn. Either way, what did we end up identifying? A new positive. Okay? So we have an entirely new question now. Okay, with that positive carbon. There is still positive hydrogen floating around. Which one should I react? Why the carbon?
It does
No.
not want to be positive.
Goes back to atom effects, electronegativity. Carbon is slightly more electronegative than hydrogen, meaning it is now not going to hold a positive charge quite as nicely. We need to get electrons to stabilize it. We already showed one source of electrons to stabilize it. Those were found within the structure. Does that permanently stabilize the structure? It does not. So what do we have to do? Look outside the structure. Where do we have a negative outside the structure? From our methanol. I see your hand, Simone. Just give me a sec. And we can have our methanol come through and attack. Should I deprotonate that methanol before it attacks? It would be a better nucleophile then. Why not? I'm under acidic conditions. I cannot make a strong nucleophile. Simone.
Why was it electronegativity and not size versus hydrogen?
Actually, that's a reasonable question. Oh, but we can kind of go back and forth on that one, actually. Size would be the first thing we'd look at. And what you'll find is we do encounter some exceptions, and in this case, we do have to run into that wall, actually. Because hydrogen, we would say because it's smaller, wouldn't be able to stabilize that positive charge as well. So we would predict it to go through and react. And yeah, under these circumstances, we could have it go through and react with something else. We're still going to generate unstable structures. This is where it comes back to what Sarah had initially suggested, drawing all possible products. Okay. So what's our product now? Did I miss an atom? I just heard some whispering. Just wanted to make sure I didn't goof something else up. This reaction. I did it again. Jeez. They just moved the table. Is this product stable? What did we end up generating? A very positive oxygen. Does oxygen want to be positively charged? No. So what can it do? Okay. Apparently a lot of take electrons from the hydrogen. Why? Why not just supply another methanol? Have another methanol come in and share electrons with that oxygen. None of those are acceptable answers. Keep trying. Sorcery is not bad. No. Why is that last arrow completely invalid? Should never have even been drawn. No. Sterics can still be forced to happen. What's this? No. Yes, it's incredibly unstable. But the question becomes why?
Because oxygen doesn't want to give up electrons.
It's not giving up electrons. It's actually accepting more.
So the other one has to share as
Well,
well.
that you could try a different hand wavy argument, but our methanol still shared electrons to begin with. Why can't it share a second time? So if it shared once, why is it not valid a second? Everything about Lewis structures. Octet rule. Octet means 8 electrons. How many electrons are currently around the oxygen? 8. It cannot accept more electrons. Right? Ooh. How can I do this without deleting everything? That worked. Right? Which means, where do I need to find electrons to stabilize that positively charged atom? Within the structure. So where's the closest source of electrons within the structure? I would argue it's even closer than something attached to it. It's the bonds immediately around the oxygen. That line represents electrons. So if you tell me hydrogen, the electrons between the oxygen and hydrogen are a heck of a lot closer than the hydrogen atom is, because the electrons are between them. Okay? Why not pull off, say, the methyl instead? Has to do with stability of those. The hydrogen can stabilize that positive charge a little bit cleaner than our carbon can. Okay? Now what happens? Because what is special now about this structure? What was that? You say it was done? Or dumb. Yeah, that was a possibility too. Kinda. What was the issue, first off, since we're on that path, of our acetals and hemiacetals? Very reactive and almost immediately go back to our carbonyls, okay, our ketones or aldehydes. This is actually a step above that. Why is this a step above that? There are 3, start talking like Elmer Fudd, 3 oxygens attached to that central carbon. Okay? It is now even more reactive. That carbon is really starting to panic and freak out and want some electrons. Where can it get electrons from the easiest? Bonds, interesting call. If we pull electrons from a bond, what happens? It's not a leaving group. Leaving groups take electrons. We're saying the carbon is taking electrons. Well, I guess you could make your argument that the carbons are leaving group. Okay. What happens to the oxygen? it would have lost those electrons, and now our oxygen has, why positive 2? Lost 2 electrons from its octet. Okay. Is that going to happen? No. Why not?
It's a very electronegative atom.
So the easiest answer is it's a very electronegative atom. Our oxygen is not willing to lose electrons. It'll share, never lose. Okay? So those electrons must stay in that bond. So we can't get electrons from the bonds. Well, if we can't get them from the bonds, what do? Move further away. Move out to the atoms. Are there atoms outside that carbon that are willing to share its electrons? We've got oxygens. Okay? And yeah, we do kind of have a pseudo-gray area there because oxygen doesn't really want to share electrons. Okay? But remember, carbon is at a horrible situation right now. It's got 3 electronegative elements attached to it. It needs that extra space. It needs those extra electrons. All right, so now what happens? Which of those electrons get shared? 3 choices. Was that top, right, and bottom? Should we choose the bottom one? Why not? It's not going back because what's happening? We're taking electrons. We're sharing electrons. Why is that the worst option?
Fair enough answer.
You can make some arguments about not looking like the product. Has to do with reactivity of our electrons again. Which of those electrons is most willing to be shared? This oxygen is sharing electrons with what? 2 carbons. What's the difference between carbon and hydrogen? Carbon is more electronegative than hydrogen, which means what happens to those electrons?
They're shared more equally.
Which means this oxygen is what charge? Relative to the others.
It's less negative.
It is less negative. If it's less negative, can it share its electrons as easily?
No.
Nope. So, does it matter which oxygen we use on the other 2?
No.
Why not?
They're the same.
They're the same. So we could try and have those electrons share. Then what happens? Too many bonds. So we'd have to break a bond. What bond do we break? One attached to the oxygen. I agree. Which oxygen? Top or bottom? Why the top, not the bottom?
Because you're pushing electrons.
That doesn't quite work. Oh, that's an interesting argument. Yeah, sure, why not?
Now it is.
Could do that. Push those electrons out. Yeah, that worked for that one. The other option is we can now also bring in our product answer. Is this going to be our correct answer?
No.
Why not? What was your choice? That would give us OH minus as a leaving group. Is that a good leaving group? No. The only time it was a good leaving group was when what? It left into a base condition with OH minus. We don't have that under these circumstances. We have acids.
Instead of conditions, aren't you going to protonate that oxygen at the top?
Exactly right. So our sequence of arrows there was the incorrect option.
Thanks
Hi.
for dragging us down that wrong road.
I didn't drive you down any wrong road.
Next time I'll speak up sooner.
Why don't we take the hydrogen from the other OH group?
Why do we not take the hydrogen from the other OH? It's a good question.
You could.
Anybody want to volunteer? I would argue you should not.
To which,
Why not take the hydrogen off? Let's draw it in purple, I guess. Does purple show up? Why not take that hydrogen off?
Oh, because we are in acidic.
We're under acidic conditions. If we pulled that hydrogen off, what charge does that oxygen become? Negative. No negatives in a positive environment. Right? So we now have this structure. What can happen? I'm definitely running out of space. We can have the electrons come back down and push out the leaving group, or We could have the leaving group get kicked out on its own, and this is a fun argument to have with people.
And then you have a charge on the carbon and carbon, right? Essentially.
Oh my gosh, I'm definitely running out of space. Should have drawn smaller. H2O, there's our OH. Or we could have done it in this fashion, right, where we had that, and everybody goes, well, that's the wrong answer, that can't happen. The product that we drew first versus this, what's the relationship?
The resonance.
They're resonance structures. It makes no difference. Okay? Under acidic conditions, we're probably going to have the leaving group leave on its own first. Okay? But officially, we're just looking at resonance. So we can go out and show our resonance. Oh man, since I already started it, got to draw it out. Almost. Is our structure stable? Nope. What's wrong with it? Positive oxygen. What do we need to do? Take the electrons. We can end up at our final product. 1, 2, 3, 4, 5, 6 steps. Okay? With 2 resonance situations within that. If you were asked to provide a complete mechanism, all of that would need to be provided with each of those resonance structures, because each of those resonance structures explains why you can advance to that step. Without those resonance structures, you don't have an explanation of why you can advance.
But that might be a question on the multiple choice, which of these are valid resonance structures?
Yep.
As intermediates?
So on the ACS, you may think, well, I don't have draw mechanisms. You don't have draw mechanisms, but they could ask which of these are valid structures in the process of making or doing this conversion. And they could go in and throw in structures that are valid structures with negative charge if you ran under basic conditions. Okay? So you do have to be familiar with how the reactions work and what individual steps you process through. Okay? Could we make this reaction go faster? Or let's try that again. Can we get the product faster? Nope. Low concentrations could work with this. We could pull all sorts of Le Chatelier type questions with this. So since you asked that, let's do it. Our favorite French chemist, we could remove water. Okay? So we could distill off the water. What else could we do? Put in excess of one of the reagents to force our equilibrium. Which reagent do we typically pick? It's usually the alcohol, because the alcohol is a little bit cheaper and technically less dangerous. Okay. I know carboxylic acids aren't that bad, but they are technically a little bit less dangerous than our alcohols. Okay. Okay. Whatever you said.
We knew which meant.
For the recording for the future.
Oh. I don't think you can hear you guys talk anyway in the recordings. So I made a typo in my speaking. Let's try that. What else could we do? Increase the yield of our product. Right? I'm not saying that we necessarily do this reaction. Heat will speed up our overall reaction, so we will obtain our equilibrium much, much quicker, but that's not going to favor products. Yes, use a different, pretty much anything. Okay. Use a different starting acid. Instead of using a carboxylic acid, let's use an acid halide or an acid anhydride. Both of those generate better leaving groups. We're going to get a much higher yield of our product because our starting material was a much more reactive electrophile. So if we can change our reagents, we can change those so that we maximize our yield and not have to go through a silly equilibrium situation like this. Okay? I sure there weren't questions because I just deleted all that. And my computer just froze. Maybe it's back. Well, the computer's back, but that's not. So we've got our reaction summary of everything. This is pretty much what I already had shown you, except this textbook where I got this slide from turned it on its edge, okay, as opposed to top to bottom. So we've got our acid halide over on this side of the reaction. There's our most reactive. Is that actually drawing? Yeah. Down all the way towards our least reactive. Okay, and you'll notice that they added nitriles into this. We've already been doing some talk with nitriles, so I decided to not bring it in with this one as it was. Okay. Questions? Super exciting. You can tell it all in your faces. We'll go back to our amines. We're going to try and whip through some of this. We've got primary, secondary, and tertiary amines. That's all in reference to how many carbons are attached to your central nitrogen. In nomenclature, how do you know that there's something attached to a nitrogen? You'll see in the name, whoops, okay, an N dash whatever it was, methyl, okay. The only reason you'll see it with the N is if the amine is not the primary functional group. Okay? If the amine's not your primary functional group, there's no reason to use the N. That's when you'll use the N. If the amine is your primary functional group, we don't have to label it as an N. We'll refer to it as an amine because it's our primary functional group. Okay? The other case where you might see it show up as an amino, okay, that will sometimes get tossed in there as well, like amino acids. Okay? There's a bunch of names. You can go through and cover that up on your own time and try and name those compounds. You can see a slight variation within those, bringing in some extra terms, some stereochemistry, all that fun jazz. Okay? I don't think nomenclature is particularly exciting to talk about anymore, so we're just going to advance. Usually act as bases. Okay? So this is where this chapter can become a bit tedious, is that our amines are almost exclusively bases. They will still act as nucleophiles, but that base characteristic plays a much larger role. So that means if at any point you generate a little bit of acid, guess what the base is that's pulling up that acid? The amine. Well, if the amine reacts as a base, do we have a nucleophile anymore? No, because now that lone pair has been reacted with a hydrogen. So in a lot of your amine type reactions, you'll end up seeing two equivalents of the amine, because one equivalent will be used as a hydrogen scavenger, pull out, grab any acids that's randomly formed. The other nitrogen or the other amine will go through and act as your nucleophile. Right? So this homework in particular is something that would be extremely tedious within sapling, which, did anybody actually want sapling questions? Because I looked at it. It's like 70 questions per chapter, non-filtered. Okay. If you want it, let me know. I'll pull it up later. Just like we could do with carboxylic acids, we ranked acidity. Guess what you can do with amines? Rank basicity. Okay, well, how are you going to rank basicity? The opposite of acids. Okay. You'll go through and do the exact same thing that you did with the acids, except now you change your perspective on it. When we looked at ranking acids, we looked at, does it form a charge? Okay, does the conjugate base form a charge? If it didn't form a charge, it was a stronger acid. Well, but what's happening when we look at a base? We could push all the way to the conjugate acid. I would argue that that's more difficult. There's a reason we shift to the conjugate base. What charge is our conjugate base most typically? Neutral or negative. We're looking at a lone pair. Okay, we draw lone pairs in our structures. What do we look at if we look at the conjugate acid? Missing electrons. That's a little bit harder for most people to process. Okay? If you can process it on that end, by all means go ahead and do it, but I think that is more difficult. So when we're looking at bases, you don't have to draw any conjugates of anything. You just look at the structure and say, okay, what's the most basic thing? Well, first off, what does that most basic thing need to have? Electron. What's going to make it more basic? More electrons. So do whatever you got to do to put more electrons out onto the nitrogen. The more electrons it's got, the more basic it is. So if we take a look at these three examples, which of those is going to be the most basic? Okay. I love how you all attempted this question. Makes me super proud inside, because what did all of you do? Put your pencil down. Nobody started drawing out the structures. Okay? Guess what? If this was your ACS exam, you just got it wrong. What did I say you needed to do? Draw your resonance structures. Oxygen has lone pairs. Where do those electrons go? Into the ring, and they sit on what carbon? The carbon immediately attached to the nitrogen, which means that nitrogen has more electrons. Take a look at that bottom one. You draw out that Lewis structure. Where do the electrons go? What charge builds on that carbon immediately next to the nitrogen? Positive charge. Okay. I didn't lie or try and trick you when I told you you need to be drawing these things out. Okay. That bottom one is not very basic. Okay. The nitrogen's lone pair is drawn into the ring to stabilize that positive charge resonance structure. If the electrons are drawn into the ring, what happens to its reactivity? More stable, less reactive. Okay? We could make the argument by looking at the pKa's. Okay, nobody's got the pKa's memorized, so it's not going to be all that helpful. But if we look at the pKa's, right, the bottom one, pKa of 1.7, what does that mean? That one's the most acidic, which means, whoops, our conjugate base is the least basic. Okay? Please draw out the structures. Okay? When in doubt, draw the resonance, see what it looks like. Otherwise, you are just taking a guess in the dark. Okay? These are a favorite ACS question because most commonly, what do students tend to have to rank? Acidity. What's the issue with basicity? It's the complete opposite of acidity. So when you look at that, you may have said, oh, that nitro group is electron withdrawing. And if this was an acid, that one's the most acidic. Right, because the electrons get drawn into the structure. But I didn't ask if it was an acid. I asked if it was a base. Okay? Spend the time to draw out those structures. Synthesis of amines. This reviews some of the stuff that you've already seen. You can look at your nitrile reagent and standard substitution. You go ahead and put on that nitrile. You can then go through and reduce that with your lithium aluminum hydride, and you can end up with your primary amine. Okay? You just add a bunch of hydrides to it. Officially in our acid-base chapter, or sorry, our carboxylic acid chapter, we can go through and convert an acid functional group over to an amide through a variety of ways. We could just go through it and add ammonia and hope it goes through. The issue with that is where is the acid relative to the amide? On our totem pole of reactivity, they're both at the very bottom of reactions. Okay? Which means if I want to convert the acid over to the amide in any high yield, I need to get that acid more reactive. How do we get it more reactive? What does SOCl2 do? Turns it into the acid chloride. The acid chloride is at the top of the totem pole in reactivity. So now all I have to do is add that nitrogen nucleophile in the case of ammonia. And what happens? Immediately do our substitution and we can get our amide. Just like we did with the nitrile, once you've got the amide, you can reduce it down, adding the lithium aluminum hydride to go through and get you to the amine.
Well, okay, so sodium borohydride not strong enough to react with that, but then is dibol?
Dibol will do it.
We'll do just the one.
We'll do a
single
single reduction? That's an interesting question with this.
Because then if you add H2O, it won't take it all the way out because you'll still have a double bond. So then it would take it back to.
Yeah, actually, I don't know what Dibol would do with this. Because if you did a single one, you'd have...
Just C with the double bond to N, so it would take it to.
It would probably take it to the imine, not to the aldehyde. Oh, if you added water, yeah, right. If you follow it up with water, you'll end up with the aldehyde.
So.
Good call. Yes. So you would have to do 2 equivalents of the Dibol.
Okay.
One of the last ones, we can put on a nitro group, okay, using nitric acid, sulfuric acid, just through our standard what type of reaction? EAS, electrophilic aromatic substitution. We can then reduce the nitro group through a variety of different methods. This slide is actually kind of nice because it gives all the options. We can do H2 and platinum. And then the other option is pretty much any sequence of metal and acid. Okay. No one seems to be consistent on which metals they go through and use, which means if you see a metal and acid in a nitro group, you're probably just reducing it. Okay. Straight down to the amine. We can do some other types of reactions. You can drop in this azide group, N3, which is a reasonably strong nucleophile. You can just do a substitution reaction to give you the azide group, and then you can reduce that down. The azide functional group, let's see if I can draw it real quickly. When it's attached to our structure, we'll have our nitrogen, double bond, nitrogen, whoops, and then we have some charges floating through here. Okay. So the azide happens to be called a Zwitter ion, okay, because it is an overall neutral structure that is charged. Okay. Works out really nicely with our reductions because what else is going to be produced after we reduce the azide? Nitrogen gas, an incredibly stable, good leaving group, okay, which will get kicked off nicely. We should be able to do this, not too bad. Gabriel synthesis, kind of a neat one. Looks a bit crazy because you got all these big pieces floating around and it's kind of panic-inducing, but it's actually pretty straightforward. Okay? What we're going to do is take a look at the functional group shown here, almost like anhydride, except we've got a nitrogen instead of an oxygen in it. That compound happens to be referred to as thalidomide, or phthalimide, sorry, not thalidomide. Okay, phthalimide. Within that structure, you'll notice the next reagent we add is what? A strong base. Okay. What is that strong base going to react with? The acidic hydrogen. Why would it pull off that hydrogen? Why is that hydrogen acidic? Notice any patterns? Answer to all questions. Resonance. Okay, we get a lot of resonance within that structure. That resonance is going to be the contributing factor to why it acts as an acid instead of having those carbonyls act as electrophiles. Okay? So it's going to be our primary driving force because that nitrogen can now do resonance within those carbonyls. That makes that our primary characteristic. What's special about this new structure that we've generated? It's charged. What charge is it? Negative. Okay, we got a big negative charge, which means it can act as a nucleophile or a base. We can now react that structure with an alkyl halide. Okay? Any alkyl halide works, but our primary characteristics, no pun intended, happen to be primary alkyl halides. Okay? Why? We're looking for minimal steric hindrance within this. Because if we opened it up with, say, a secondary or a tertiary alkyl halide, what could potentially happen? Okay. I'll draw one out. What's going to be the issue with using a tertiary alkyl halide? That's chloride, by the way. The thalidomide, that word is a big negative, which means it can act as a nucleophile. It can possibly act as a base. What happens when we shift up to tertiary alkyl halides? We start to increase the likelihood of the E2 mechanism, which means we would get the elimination happening in this, not the substitution. Okay? So if we really want this reaction to work, the primary alkyl halide is our best bet. We've got minimal steric interference, which means our structure will act primarily as a nucleophile. We can chase out that halogen, and we now end up with our nitrogen with an alkyl group. Okay? Oh, fancy that. Look, we've got an amide now with a carbon or extra carbon chain attached to it. It seems a bit tedious to go through and do all of this. Okay? What is now unique about this structure? What happens if I add another base? Is there an acidic hydrogen anymore? No. So what could potentially occur? It can attack the electrophilic carbonyls. And what will end up going through and happening, okay, is that we can then cleave that ring open and chase the little amine group out. Kind of neat. The net result is that what have we formed? In either circumstances, we have an amine. Be a little bit more direct with that. Type of an amine do we have? We have a primary amine. It's an awful lot of work to go through to get a primary amine. Why do we have to go through all of that work to get a primary amine? So do I have more space on the next page? I do not. Why don't I just take ammonia and that same alkyl halide? Remember, the nitrogen's a good nucleophile. Why don't we just do it this way? Okay, it can be charged. That's fine. But what will end up happening? We've got a strong acid which could then be deprotonated, and we'd end up with our primary amine. So why bother to go through this Gabriel synthesis if this works? Because it doesn't work. What doesn't work about it?
It will react.
When we run this reaction, how much do we have of everything? Small amount, lot amount. Lot amount. We've got a lot of both of these reagents floating around. Remember, when you run a reaction, you're looking at mole levels. Okay? Tons and tons and tons of molecules. If we go through and take a look at our alkyl amine, it's kind of a neat structure in that it is still a nucleophile. And what else is still present? What did I use? Chloride? I use X. Electrophile. What happens? Reacts again. Okay? And after that goes through its sequence of reactions, I end up with what? I got my secondary amine, which could then do what? Could react again. Right? So if we react under these conditions, we don't get a clean primary amine yield. We get a big mixture of primary amine, secondary amine, and tertiary amine. Okay? So our issue with our amines is that they are exceptionally good nucleophiles. Okay? So the only way that we can go through and get a primary amine is if we can limit its reactivity and prevent it from reacting through with something else. The Gabriel synthesis does a pretty awesome job of that, because our nitrogen, in this case, only has one reactive site, okay, on the phthalimide. All right, and then when we go through, all we're really doing is then cleaving off the protecting group, if you will, as the rest of that structure. All right, and we can do it with just straight acids. You could also go through and use hydrazine, right, which is a fun chemical to use. All right, so that's why we use the Gabriel synthesis. The other common one that gets tossed around a whole lot is that, remember, we can take a ketone to an imine, okay, by just reacting those two. Remember, you got a carbonyl, add a nitrogen source, boom, you now have an amine, okay, every single time. Well, how could I turn this now into an amine? What is the amine? An amine is a single bond to the nitrogen. What do I have to do? Close. Add a hydrogen. What type of hydrogen? A negative hydrogen, a hydride, and a reaction known as a reduction. So what is this referred to? A reductive amination. Should really be amination reductive, but that's where the term is coming from. Okay, you're putting the amine on, and then you're reducing it. Okay, that is a very common one to pop up as well. So you need any kind of reducing ability to go through and convert that across to the amine.
If you did Lindlar, would that also reduce?
I'm not positive on that. Lindlar, I think, is too selective, because Lindlar goes after a triple bond, right? So I don't know that it would work, because it won't react with alkenes. Okay? So as our overall summary for your amines, okay, you've got all this fun chemistry. We talked about the azide very briefly. You've got the Gabriel synthesis. You've got the reductive amination. Okay. Once you've gone through and done this, you can then selectively work your way up to secondary or tertiary amines by going through and doing selective or reductive amination again. Okay? So that way you can be very careful about what R groups show up on your tertiary amine. And you do that by controlling the carbonyl in your reductive amination. Okay? How many carbons are in that carbonyl? That's what's going to transfer across. Okay? So all sorts of fun results within that. I think I can whip my way through this one. Your diazonium ions, these commonly pop up again in the lab. Anybody know where your diazonium ions are most commonly found? I wouldn't be surprised if Megan knows, Teresa knows, and Christopher knows.
What was the question?
Where do our aryl diazonium or molecules tend to show up? They were one of the first dye molecules ever discovered. And they range, depending on what aromatic groups you use, range in color from kind of a burgundy color to your bright, I'm not sure what to call that, it's not salmon, red salmon, down into your browns and purples as well. Okay? So they're kind of neat for that purpose. Relatively simple chemistry once you've got them formed. The formation of them is a bit tedious, and I'll end with drawing that mechanism out on this next slide. It's a bit long. So here we go. We'll start with the nitro. So we've got an amine with our aryl group, and we've got a nitro. Sorry, not a nitro. Sodium amide. Sodium, what is that? I don't know what to call it. Let's call it NaNO2, NHCl. When you look at that, what do you see? See an acid. Okay, so we can change our focus to it being H+. Now what do you see? Positive charge where? On the acid. Okay, so we've got our positive charge. What do we need to find now? Our electron source. Where's our negative?
Nitrogen?
Good answer. Which nitrogen? What type of bond do we have between sodium and NO2? It's an ionic bond, which means sodium comes off as what charge?
Positive.
Positive, which means the other one is? What did you just find? A negative. So our negative is somewhere in that NO2. How do we know which of those atoms is the negative? Draw it by using Lewis structure rules. Yay, Lewis structures. You should end up finding out that you end up with this structure. Whoops, keep drawing that positive. Your negative comes over, picks that up, and we end up with and we also have our aryl amine again. So we did all of that, and what did we end up doing? We neutralized everything to make it even more difficult to find stuff. So, where do you want to go now? Next most reactive thing, which would be what? What do you see? It's not really an amide. There's no metals anymore. What did we say amines act as? A base. Do we have an amine?
Yes.
So we have an amine. This is now going to act as our negative, okay, which can be either a base or a nucleophile. So what does that mean needs to happen in our other structure? We need to find positive. Where's our positive? Why the nitrogen? 2 electronegative elements, and we have a nice pi bond to break. Very similar to, say, maybe what functional group? A carbonyl. Okay, so we can get that nucleophilic attack. And don't quote me on this mechanism either. It'll get you close enough. Because of time, I'm trying to skip some steps. What's the issue with what we've got drawn here? We have a negative charge. Under what conditions were we running? It was acidic. We added H+, HCl. So we'll go ahead and pick that up right away. Call that 2 steps. There's our aryl. We'll call it 3 steps. I'm going to take that nitrogen down to the neutral stage. So we added a hydrogen, lost a hydrogen. Now what happens? What gets protonated? Okay. Oxygen's a reasonable place to go ahead and get protonated, so let's go ahead and do that. I'm going to get out of the corner here in just a second. If our oxygen gets protonated, what's unhappy about that? It has a positive charge, so what can we do? Find some electrons. Where do we find those electrons? In the bond. But then that nitrogen has a problem. It's a little worse than that. It's not just that it becomes positive. It loses its octet. So we can't let it just lose its octet. We have to fix that. How can we fix that? Sharing electrons from... Why the nitrogen, not the oxygen? Oxygen can do both of those. Why can nitrogen hold the positive charge better? It is less electronegative than our oxygen. There's our double bond. We're also going to lose that hydrogen as a secondary step. Still has its lone pair. Now what happens? We will go through and protonate that other oxygen. We still have acid around. What does that result in? A great leaving group. So we can try and take electrons away, but then what happens to that upper nitrogen? Missing electrons. So our bottom nitrogen comes in, shares those final electrons, and we end up with our azo group, our diazo group. Okay. Definitely went through and skipped some steps with that. Ultimately, what you're responsible for is that I can't remember what the name of that is. That negative NO2 will go through and swap that out, and we should end up with our diazo compound. 10? Oh, all the steps. So yeah, mechanistically, we got 1, and I definitely cheated on some of those steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, probably around 10 mechanistic steps. Okay. What you're responsible for knowing is that reagent, our NO2, everybody got that copied? If you're going to copy it, is going to go through and give you your diazo compound. That reagent, I was almost positive, whoa. I was almost positive we had talked about that second step, but apparently not, because anybody or everybody I've talked to has said they don't recognize it, and I can't find it in my notes. But that secondary step can happen. Why is that a nice step to occur? Just adding a halogen to the ring doesn't make that a good step. Why is that a good step? How is that a good step? We end up with nitrogen gas as a leaving group. Phenomenal leaving group, that facilitates this reaction. Okay? So I'll end it with that. To go through and do that, though, you need the copper to kind of mitigate some of that nucleophilic characteristics. What's that? Yeah, well, copper or just this? Yeah, copper, well, that's the Gilman reagent. So copper in the presence of your diazo can go through and do this little fun chemistry. So what's the next day? Wednesday. Wednesday we'll finish up the rest of the slides. I've got a Hoffman rearrangement that I will show as a mechanism in class, just kind of written into the slides, or sorry, written over the top. And then we are officially done with new material, and it's just ACS practice. Along the lines of ACS practice,